There we go. Let me make sure this works. Okay, so welcome to week 2. We're going to be doing, we're using this manual, the Ham Radio Manual, and we're going to be covering Chapter 3 and Chapter 4. So after I wrote the syllabus, I realized, as I was reviewing 3, I realized it was pretty in-depth and pretty, if you haven't been exposed to the concepts, they may be, it may take you more time to absorb it and learn it. So I thought I would do half of Chapter 3 and half of Chapter 4 today. And then next week, I will do the other half, the second half of Chapter 3 and the second half of Chapter 4. So I'm going to kind of mix it up a little bit, but it will help you not be so overwhelmed with any one particular topic. Because I don't want you to get partway through and go, oh, this is really hard, and just give up. So, and you will have the benefit of the recordings too and the book to kind of help re-emphasize it. So Chapter 3 is on electricity, components, and circuits. Okay. So, one other thing I wanted to mention about the book. They'll have, there's test bank questions, there's categories, they call them elements. So there's like T5, and then it'll have a number by it, A01, A02, and so on. And they'll ask you questions. Like, what is this? What is that? And they'll ask a bunch of different things. And as you go in the chapter, you'll see, I'll just give you an example for the first paragraph here on 3-1. The first question, T5A01, is current and voltage. And the question is, electrical current is measured in which of the following units? And then you start reading in the paragraph, it says, electrical current represented in equations by the symbol I is the flow of electrons. And then T5A03, what is the name for the flow of electrons in a current in electrical circuit? The name of the flow is current. So that's your answer. So you can kind of see it's got the number in bold in little brackets. That's the answer to the question. So it kind of helps to go, okay, what am I supposed to learn here? What's relevant to the test? So and then I've gone through and like circled it in my notes. So you might circle or make notes or something like, this is the question, here's the answer. And so that'll help you kind of know what are the topics that are important as we go through here and as we look through the book. That's kind of how the format of the book is. So, all right, so there is a basic formula in electricity called Ohm's law. I'm going to kind of I'm going to jump to that for just a moment. It's 3-5. Okay, so if you look at 3-5, it's got E and I and R in a circle. And the way I learned it in physics, because I learned this part in physics, E equals I times R. So E stands for electromotive force, which is volts, okay, equals I. I is the symbol or the letter they use for amps, which is current, and then R is resistance. So you have volts equals amps times resistance. So I'm just going to give a couple of examples, and then it's just basic multiplication and division. So once you understand the formula and like how it works and what the letters mean, then it's a little bit easier to understand. So I brought a little black whiteboard here. I'm going to just do a couple of examples. Okay, so here's the formula. E equals I times R. Okay, so E is volts, I is amps, and R is resistance. So I like to think of this in terms of like water, okay? So let's say you got a water hose. There's two different types of hoses. There's like your garden hose, which is like a small diameter, puts out a little bit of water, and then you have something like a fire hose that's a big diameter, puts out a lot of water, right? So volts, see if I can, amps is like the flow of the electricity. So this would be like electrons flowing through the hose. So think of this as like your water. Okay. And the amount of flow is like your resistance. So volts, let's say you have a 3 amp fuse and you have 12 volts. So like a car battery, for example, is 12 volts. So if you want to solve for R, how many resistance is that? You just take the 3, divide by 12, take the I over here, so it would be E equals I times R, and you take the I and move it over here, so it's E divided by I equals R. So if you were to say 12 volts with 3 amps equals 4, and this is ohms, and the symbol for ohms is an omega. That's a Greek letter omega. You'll see that on speakers, for example. So on speakers, they'll have like an ohms rating on the speaker. That's the amount of resistance the speaker puts out. And so they'll give you a problem like, okay, you have a 12 volt circuit and 3 amps flowing through it. What's the resistance? And the answer would be 4. So if they say you have a 4 ohm circuit and a 3 amp of current, how many is the volts? Then it's 12, and you just multiply them out. So they might give you these two and solve for that, or they might give you like this one and solve for the R. So it just depends on what it is they're asking in the question as to how you divide or multiply. So that's kind of the basics. It's called Ohm's law. And there's another one, E equals IR squared, which is watts. So volts, actually it's watts, E equals IR squared, equals, it's volts, it's watts, excuse me. Watts is a measurement of power. So I times R is volts, so it's volts times resistance, or time. Well, that's watts, it's resistance. That gives you watts. So like, let's say a 100-watt bulb is, let's say, 120 volts. How many amps is flowing through that? So you would divide, well, let's say it was 100 volts for the sake of argument. You would divide 100 or 10 volts, then it would be 10 amps flowing through there. I'm not explaining this very well. Let me start over. Watts is a measurement of power. So like you have a 100-watt bulb. So watts equals volts times the resistance, or the amps. So anyway, that's another formula that's in there. It's in the book a little bit, but I wanted to jump into that just a little bit because I wanted to explain the different units that are important. So let me go back to the intro. Hey Palmer, can you give me the multimeter? Is it on the table over there? Okay, so let me go back to 3.1. So we've talked about amps. Amps is like the flow of current. So that's like the amount of water in your garden hose, okay? Voltage is kind of like the pressure or the force coming out of your garden hose. Thank you. So as an example, for example, in your water pressure in your house, it might be like 400 psi coming in from, say, the city water, and they have in your house, it's called a pressure reducer valve, a PRV. And you'll look at that on your main shutoff of your water. There's a little PRV that decreases the pressure down from 400 psi to 100 psi, because the pipes in your house are only rated at 100. If you put too much in, it'll just blow your pipe. It would be like trying to put a fire hose up to your sink. It's not going to work, right? And it would blow things up. And so you have to introduce resistance or a pressure reducer valve to reduce the pressure. And so that would be like a resistor in the circuit. There's a lot of current coming through and you want it to go slower so you don't blow your fuse. So that's kind of the concept. So the pressure would be like the volts, and the amps would be like the amount of, so that would be like pressure per square inch, PSI. That would be like volts. And then amps is like the flow of the water. And then R is how much resistance is in there. And then you get your total volume of water, or amp hours they call it. Amps, like a battery, like your phone has a certain amount of battery that it can hold, usually like a day or two charge. So that's kind of like the volume of water behind the like battery or whatever. And so so anyway, just remember E is electromotive force, that equals volts, I is amps, and then R is resistance. So those are kind of the three things you need to know. And so TD704, what instrument is used to measure electric current? An ammeter. An ammeter is measuring the amps or so instead of amp meter, it's ammeter. That's the second one. There's polarity, there's positive and negative. Okay, so for example, I have this multimeter. You may have seen these. Maybe your HVAC technician or somebody comes in to solve your problem, or maybe a car guy, he comes in, he gets this, he pulls off these little probes and he tests circuits to see what's going on, and he measures the amount of electricity. So red is positive and black is negative. So that's important to know. The electrons always go from positive to negative. Okay, so negative is the ground. So ground is the earth. So the black is always ground, it's always touching the earth. So your house, for example, there's a grounding rod attached to your main breaker, and it goes straight into the ground. So the way I think of it is the electrons start up in heaven and they go down to earth. They want to go to mommy earth. They want to go to mother earth. So when the cloud strikes, there's clouds, and the way it works is the clouds are like circulating like this. There's air that's going up and down and up and down, and as the air collides with each other like a high front and a low front, it pulls off the electrons from one side and puts them on the other. And that's the definition of a battery. Electrons on one side and not on the other. And that's called electromotive potential, potential energy to transfer electricity from one side to the other. And that's what induces a current. So when you have a lot of electrons, you've got the cloud that's charged, so it's like a big battery full of electrons. And remember the story of Benjamin Franklin, how he discovered electricity. He was like, hey, I see this lightning up there. Maybe I can use it like a lightning rod, and I can fly the kite, and it will hit the kite and then take this, it'll follow the path of the string down to the key on the doorknob, and it'll go down to ground. And so he flew the kite and started discovery of electricity. And so it's kind of like that in the clouds. The clouds are like the positive battery, and the earth is negative. And so when it's high enough, the distance between them is such that it can strike and the lightning will pass through. So lightning is just the flow of current from the clouds to the ground. So it's called cloud to ground lightning. So the electrons always flow from positive to negative. So in a circuit, it's always going to go from the red to the black. So when you're, say, jump starting a car, this is important to know so you don't shock yourself or introduce a spark that could cause an explosion. So when you get a jumper cables, they always tell you, let's see if I can remember how to say it. You always touch the ground first, I believe. Yeah, because it has the battery can give off explosive gases if it's bad, and nowadays they're sealed to a pretty low risk, but there is a risk that the battery could have a leak and it could have some explosive gas. So they always tell you to touch the ground first, then the positive last. And the ground can be the chassis of the car, and the car's rubber, and it can go insulate from the ground. And so you always attach the positive, and then negative, and then positive, and there's a certain order you do it in. And so the idea is you want to connect the good car last, because the bad car is the one more likely to have the gas. So if the one that needs the jump, you always connect that positive first, and then the one that doesn't need the jump last, so that you don't have the chance of a spark with the gas exploding. So that's a little tip for you on jump start. But a multimeter looks like this, and this one's a little bit fancier. They have an example in the book, and it's in, let's see if I can find it. It's on 3-4. They have a more basic version of this on 3-4, and it's on figure 3-4. They measure volts and ohms or resistance, and they have a continuity one. So this one, there's a symbol for V, so that's volts. So when I turn it on, it can measure volts. And there's millivolts, which is 1,000th of a volt. Did we go over, I think we went over the metric system last week? Yeah. We did? Okay. So like centimeter it takes 100 centimeters to make a meter. So you think about it takes 100 cents to make a dollar. It's a fraction of the dollar. Mill is the same. It's a fraction of a volt. So there's an MV here for millivolt, and there's a regular V for volt. So this would be to measure your volts of your battery. If you want to measure the current flowing through, you would turn to the A for the amps, and it would tell you how much current's flowing through there. So there's amps, milliamps, and then there's a little, it looks like a U symbol, but it's a mu in Greek, which is micro. It's 10 to the negative 6. So there's a microamps, a milliamps, and a amps. So you turn it to whichever one you want based on how much current you think there's going to be flowing through it. those are the two ones that are important. This one happens to have a little symbol of a capacitor, so it will measure capacitance. It also has, it says it has, yeah, this one, oh, it has a hertz, Hz for hertz, which is frequency, so you can measure frequency. So for example, in your house, it's 120 volts. There's two different types of currents. There's alternating current and direct current, AC and DC. Not to be confused with the band by the same name. Okay, so let's go to 3-2. It's got an example here, a drawing of the AC and the DC current wave. Okay, so if you think about AC current, that's alternating. So let's say this little boom here of my bike is like a graph, and this is 0. So the current starts, you induce a current, it goes up for positive, has a little hump, and it goes down back to negative, and then it goes down to 0, and then back down to negative, and then back up. So that up, 0, 0, and down and back up, that's one cycle. So that's 1 hertz. It does that one time, that's alternating current. Direct current just goes from 0 to positive, stays there over time, and then you turn it off. So like a flashlight, you have direct current, you have a DC battery, you flip the switch, it goes on for as long as you leave it on, and when you turn it off, it just goes back down to 0, and that's it. So that's direct current. So you've got an example here of the graph. It's either like a little up wave, and that's it, or it's a sine, well, it's cosine wave, sine, cosine, and it goes up and down. So that's alternating, so the current will go and switch between positive and negative flows. So let's see here. So a lot of small electronics, like your phone, anything that's portable, usually uses direct current because it's a small amount of current that it's needed, and it's just simpler and easier. So they use direct current in batteries and any kind of thing that takes a battery. Most of your household appliances will be AC, unless you have a transformer to convert it from AC to DC. Okay. So there's different ways you can connect circuits. There's what are called parallel and series. And on 3-3, there's a diagram of that using simple light bulbs. Okay, so I'm going to show you, just illustrate with this example here. On 3-3, you've got the bulbs labeled 1, 2, and 3. There's an A part of the diagram above, and there's a B part below. So above is the bulbs are connected in series, and below they're connected in parallel. So you can do this with batteries. You can do this with any kind of load, whether it's a light bulb or batteries. So for example, in the top diagram on number A, this is how you would wire up batteries. You would substitute the bulb for a battery if you want to increase your voltage. So for example, a small AA battery is 1.5 volts. Most battery cells are between 1.2 to 1.5 volts, and that's the maximum you can get out of any particular cell. So well, then how do you do like a 12 volt or an 18 volt cordless drill or something? How do they do that if you only have 1.5 volts in a cell? Well, they hook the cells up in series, and it adds the volts together. So if you have two 1.5 volts or two AA batteries, you can get 3 volts maximum. And if you wanted 6 volts, you would have to have 4 AA batteries. And if you wanted to have 12 volts, you'd have to have, what is that, 8, right? So 8 times 1.5, 12, yeah. So you have to have 8 AA batteries in series in order to get 12 volts. So that's what they do in a car battery. They would have at least 8 cells in your car battery. So when you look, you see like 8 little, it's usually lead acid. So there's plates of lead there with the battery acid in the electrolyte is called. And so you add those 8 cells together in series, and it adds the volts together. So if you take 1.5 plus 1.5, that's 3 volts. You double that again, and you get 6 volts. You double that again, you get 12 volts. So you would need at least 8 cells in order to get 12 volts. So that's how you would add it. Now, if you want long-lasting battery, like let's say 1.5 volts, you wanted to make it last instead of like 1 hour, you want it to last 10 hours. You would hook up a whole bunch of 1.5 volts in parallel. So that's figure B. And what that does is it makes the current last longer. So it's called milliamp hours. So it's the amount of amps or currents flowing through it over a period of time. So you just increase the size of each cell. So like a car battery, 12-volt battery is a lot bigger than a AA battery because those cells are a lot bigger, so it can last longer. So, and then in 3-2, they have an example of measuring, they compare the pressure to the flow of electrons. That's what I was talking about with the garden hose. So you can measure pressure, which is PSI, or amount of volts. You can also measure the flow of the electrons, that's be the amps. You either measure it with a voltmeter, so you'd either change it to volts, or you can change it to amps, and it can convert to an ammeter. So this is an ammeter or a voltmeter. That's why I call it a multimeter. You can measure different types of things. So also you see in the battery, they have an example of a AA battery. The little bump on the battery is always the positive, and the flat spot is always the negative on AA, C, D batteries, and so on. So the bump is always going to be the positive, the red, and then black is always going to be the negative. And so you'll see the current flow direction goes from the top of the positive through the meter and then down to the negative. Okay, so let's see what else here. Oh yeah. Okay, so let's see if I can say this correctly. T5D13 on page 3.2. What type of circuit is DC current the same through all components? So it's either going to be series or parallel. 13. And then if you look at 3-3, they kind of give you the answer. If two or more components such as light bulb are connected in a circuit, so they all have the same current, that is series. So if you look at the part A on this 3-3 figure, it has the letter I. That I is amp, so that's current. So it's the same current through each of these bulbs. It might be 3 amps here, 3 amps here, 3 amps here. So it's the same in series. And then the same question is going to be the opposite for volts. It says, in which type of circuit is the voltage the same across all components? T5D14. And that is going to be parallel, which is this one. So they have the letter V here. So all the volts are the same across a series in parallel.
So going back to that previous question, is that why they say you should replace your light bulbs on a Christmas tree? Like, if you have one light bulb blow out, you should replace it. Otherwise, the rest of them will go more quickly, because it seems like if one of them blows out, then you've got more current flowing through all of them.
Yeah, there's two different types of Christmas tree circuits. One of them are wired in series like that, so if one blows out, the rest still function. That's the advantage. In the series, this is the way the old circuits used to be. One blows out, the rest, even though they're good, will just blow. You've shorted the circuit. So most Christmas lights now are designed so that they're in series, so that for convenience, So they actually have an extra wire going here. Sometimes you'll see 3 wires going in. One of them is the line for the volts, and the other is kind of extra to pass it on to the next one. But yeah, I'm not sure about the volts and the amps as far as the actual light bulb and how that affects the lifespan. I'm not sure about that, but that does bring up a real easy example. In series, you take out bulb 2 and bulb 3 is not going to work, or bulb 1, because your circuit is now shorted. So but down here, you could take out bulb 1, 2, or 3, or you could take out 1 and 2 and 3 would still work, or you could take any one of these or any 2 of these and the other ones would still work. So
so if you were to bypass bulb 2, you're effectively increasing the current in the circuit, right?
Probably, yeah.
If you take out one bulb, then there's more current going through the circuit.
Yeah, the volts is going to be the same in the series in B though, but yeah, in parallel, the current's always the same, but the voltage is going to differ. So the voltage might increase or decrease in the top one. If you take out bulb 2, you might have more voltage. You're not going to have a voltage drop. So you have a voltage drop with each load in series like this, and that's the reason why. This isn't really a test question, but I just remember this from my physics class. They were explaining, why do they use high voltage lines? Why are they high voltage? And it's because it has to do with E = IR. So the voltage over time is increased resistance. So by the time you get to the end of the line, there's a lot less voltage. So in series here on the top, by the time you get to bulb 3, there's a lot less voltage. So it might be a little dimmer than the bulb 1 and 2. So you lose, you get a drop in voltage every, and even the line itself has resistance. So whether it's copper or aluminum or whatever you're using to transport the electricity, whatever wire that is, it's going to reduce and you're going to have resistance over time. And the longer the wire, the more resistance. And so when you're transmitting over hundreds or thousands of miles, you don't want a lot of resistance. And so what they do is they increase the voltage, so then the resistance is minimal and allows them to transmit power more efficiently. That's why you have to have transformers, because you have to go back to a lower voltage to actually use it, because you don't want to have a 100,000 watt light bulb in your house, you know. Anyway, that's kind of a side note, not related to the test, but kind of an interesting reason why they do that. Okay. Okay, so what can damage a multimeter? 3-4. Okay, so T7D06, the first question there, right here, it says what can damage a multimeter? Basically, too much voltage or too much current. So like I was telling you earlier, this one has a good example because they have 2 different red things you can connect to. They have a milliamp and then they have a 20 amp. So this one can handle more current than this one. If I was measuring like a watch battery or a small electronic component, I would be using the milliamp. If I was measuring my house voltage, I would use the 20 amp. Most house currents can go up to 20 amps. Most circuits are 15, some are 20, but they usually don't go over 20 for your house current of 110 volts. But if you're having like a watch battery, it's 3 volts, it's very little current, you want to use the smaller one. But if you put the smaller one in and then plug it into your like electrical outlet to measure, it might blow a fuse. These have fuses in them to prevent you from ruining your whole meter. So what could damage it is too much current, too much amps, or higher voltage than it's rated for. All right. Also, well, yeah, I won't go into that. All right, so I've talked about Ohm's law a little bit. So on 3-5, you've got T5D01 and 2 about in the middle of the page. They say, what is the formula used to calculate current? What is the formula used to calculate voltage? What is the formula used to calculate resistance? So it's either E equals I times R for volts, I equals E divided by R for amps, or R equals E divided by I for resistance. So it just depends on which one of these you're trying to solve for. The answers are right here. T5D01, those are the formulas. So, and then on figure 3.5, they have the E equals IR, but they also have another one, P equals IE. So P is power, that's like your watts. And then I is your current, and then E is volts. So it's the same thing, P equals I times E, so pi, PIE. So you just remember PIE, P is power, I is amps, and then E is electromotive force or volts. So if you want to know how many watts is in the light bulb, you just take your amps times your volts, and that's your power. So for example, a circuit, I should just do the math. So let's say you had, I'm going to get my calculator out just because I don't.
P is power, I
is amps, and E is EMF or volts. Electromotive force is volts. So just think pi. So let's say you have 110 volt circuit in your house. No, we'll say 120. So it's 120 volt circuit times 15 amps. That's 1800 watts. Okay. So 120 volts in your electrical socket in your home, and you take that times 15 amps maximum. That means you can have 1800 watts. So you plug in an electrical heater or a hair dryer, the most you're going to have is 1800 watts. Probably most of them are rated 1500 watts just because you have a little buffer. Okay, so if you plug in like a 2000 watt thing into your circuit in your home, it's going to blow the breaker because it's too much. And my thing is beeping at me. Okay, so it'll have a maximum of 1800 watts of power. So that's why you can get, like 100 watt bulbs. Well, these are LEDs, so they're maybe 15 watts. But let's say you had 1800 watts. That means you can handle most 18 light bulbs of 100 watts in one circuit. And if you want to hook up more than 1800 watt bulbs, you'd have to have a new circuit. Otherwise, you'd blow your circuit. You'd blow your fuse. So that also tells you the size of your circuit. So you don't have to know the circuit size or anything, but I'm just giving you an illustration. So like in our house, we have 6 lights here in this room. If those are each 100, which they aren't, but let's say they were for sake of argument, that's 600 watts just for this one room. And if I wanted to put, like 3 more rooms, 6 times 3, that'd be 1800. So I wouldn't want to have more than 3 rooms worth of lights or load on a circuit because it would blow it, because the amount of thickness of the wire is only 15 watts. So that's like the size of your fire hose. So think of it this way: you go out to water your lawn and your garden, and you may have seen those like tubes that will have little sprayers come out on them, or let's say a zone in your yard. Each zone might have 3 or 4 or 5 sprinklers, but if you were to hook up 20 sprinklers and try to turn that zone on, you'd have low water pressure. You wouldn't be really doing anything. It's the same thing with electricity. You don't want to hook up too many loads onto one circuit, or you're not going to have any pressure to put out the load. So that's probably more than you needed to know, but it gives you an idea. On 3-6, they have a bunch of examples. These are just your basic volts equals amps times resistance formulas. So 3-6, they have an example of a little battery and a 10 ohm resistor, and you're measuring the amps. So they give you 2 of the 2 values they want you to solve for the volts. So it's a 2 amp, you measure it and you see 2 amps of current going through your battery. You know you have a 10 ohm resistor. How many volts are going through there? Well, it's 10 times 2, which is 20. So it's a 20 volt battery. So that's problem 1, and they have 2 other problems similarly. So the next one example is you have a 12 volt battery, you have a 6 ohm resistor. How much current is going to flow through there? Well, 12 divided by 6 is 2, so there's 2 amps flowing through. So there's a bunch of examples here. You can practice that, but they're pretty straightforward. Same thing with power. On 3-7, they have examples of power. So for example, you have P equals I times E, or EI, however you want to say it, 13.8 volts, and you have a 10 amps of current. What is the load? It's 138 watts of power going through that circuit. So you just multiply the volts times the amps, that gives you your watts. So, and they have another example here, 12 volt circuit, 2.5 amps, that's 30 watts of power. So you might have an electrical 12 volt heater, let's say in your RV, or a portable heater in your car, or whatever, it's 12 volts, and you're going to only do 2.5 amps. That means your heater can only be 30 watts. It's not going to put out a lot of power, but it may heat something, So, okay. Now I'm going to introduce the components, and then we're going to stop on this part, and then we're going to go into chapter 4, because the next one is a little bit more. I'm just going to tell you the names of some of the basic electrical components and introduce it to you so you've heard it once, and then we'll review it next week. We'll begin next week on 3-8. So the first one on 3-8, they give you some electrical components here in the picture. It's figure 3.7. On the left, there's different types of resistors. Okay, so resistors are usually like this round cylinder looking thing. And just so you know, I had to learn this because I took an electrical engineering class in college. It was one of my requirements. And it was kind of fun, but I'm glad I'm not an electrical engineer because it was pretty complicated. But you notice on here they have little lines on the resistors. They're colored lines. They actually color them, and they have different thicknesses, kind of like a barcode. And if you add them up, it tells you how much resistance is on it. They're usually labeled on it, but the color and the bands actually tell you what the resistor is. You don't have to know any of that, but I just wanted to let you know about that. Another thing you might see on circuits is this little thing on 3-8. Those are capacitors. Okay, so resistors, by the way, the measurement of resistance is ohms. It's the omega symbol. And then capacitors, the measurement is called farads. So they're measured in farads. They're usually picofarads. Pico is 10 to the negative 12th. They're usually small amounts, microfarads, picofarads. So it's farads is the unit you need to know for capacitance. Think of a capacitor as like a mini battery. It charges up, it stores electricity, and then it can discharge it. So a capacitor is just storing electricity. And there's 2 ways you can store electricity. You can store it in an electromagnetic field, or you can store it in a magnetic field. So these capacitors, there's disc capacitors that look like a little disc with 2 little wires coming out. Sometimes they are like a little battery looking thing. and sometimes they're small or big, different sizes. So those are capacitors, with the letter C for the symbol. 3-9 shows you inductors. Okay, an inductor, there can be an air inductor, so it's just a coil of wire with air in the middle, so it's just empty, just like a big spiral with nothing in it. Or you can put a ferrous or iron core in it. It can be a disc like a donut or a toroid shape. That's the geographic term, toroid. It's like a donut. So they can wrap wire around a donut. They can wrap it around an iron coil, and that's called an inductor. If you put two inductors close to each other, you can transform and increase or decrease the voltage, and that's called a transformer. The next component, 310, those are adjustable circuits, variable inductors. So what they do is, let's say this inductor here, you can see this little donut with like little wires going around it. So think of this as a clock. So the coil goes in here at say 2 o'clock, comes out at say 3 o'clock on the other side. So if you were to have like a pointer and you were to connect the circuit here, here, or here, you have increasing number of loops. So the increasing number of loops would be increasing resistance, decreasing number of loops is decreasing resistance. So that's what they use in a volume control. So when you turn up the volume, you're increasing the resistance or decreasing the resistance. So turning up the volume is decreasing the resistance, allowing more electricity to go through. Turning down the volume is increasing the resistance and allowing less to go through. So you put this inside of a nice little spinner, or it's called a potentiometer pot. We call it potentiometer. So the potential energy goes up or down. Adjustable resistor, variable or adjustable, and that's how you have volume controls. Now a lot of them are electronic, but in the old days they were just little knobs you would turn. So that's how they do it, is they just increase or decrease the resistance. And transformers, that's to transform AC to DC or DC to AC. That's when you plug in a little adapter to decrease or increase your current. So like when you plug in your phone, there's usually a little adapter that hooks to the USB. The USB is like usually 3.5 volts. And there's two types. There's like the fast charging version and the slow charging version. So the slow charging version is like 1.1 amps, and the fast charging version might be like 2 amps. So you can imagine 2 amps, it's like your fire hose versus your garden hose of 1 amp. So it'll charge faster because you got more electricity flowing through it. So same sort of thing applies, like in USB for your phone and that sort of thing. And and I'll touch on one more component, which is a transistor and a diode. Okay, so a diode, LED, who knows what LED stands for?
Light emitting diode.
All right, diode, light emitting diode. What does a diode do electrically? What is its function?
I think that it can only flow electricity, and it can only flow in one direction.
Right, it's a one-way valve. So it goes out, but it can't come back. So the function of a diode is to get the electricity out, and so it doesn't backfeed. So in your sprinkler system outside, when I was in Denver, I think they might, I'm not trying to remember if they have the requirement here. It was a city code. They had to put in a backflow preventer, and the idea is you don't want that water to go backwards. And the reason is if you have chemicals on your lawn, somehow that water and the chemicals could go back in your lawn and then go back into your culinary line, and they can get in your water, and then you got chemicals in your drinking water. So they have a backflow preventer preventing it from going back. We have the same idea in electricity. You don't want the electricity to go back and cause problems or damage, so they put a diode in to make sure that electricity only goes one way. And a light emitting diode is one that produces light when electricity flows through it. And of course there's different colors, red, green, blue, indigo, violet, this sort of thing, different. And a fuse, I'm gonna go to fuses, 3-13, and this is just gonna be an overview. I'm gonna cover this more next week. But what is the function of a fuse? Or a breaker?
To give up its life.
Yeah, give up the life. But why do they put a fuse in? What's the purpose? Right.
The breaks that prevents you from running your device, whatever you're plugged into.
Right. It's kind of like it's emergency relief. Like if you put too much through accidentally, it'll burn up that little piece of wire, and then cause it to snap or break the circuit before it would break your circuit behind it, like before it would blow out your light bulb or your stove or whatever. It'll just break the fuse. So they have, breakers that will just flip back and forth, and they're spring loaded. So they have an example of that on 312. All right, so I'm going to skip over the rest of it. We'll come back and do the second half of chapter 4 more in depth next week on some more of the terms. But the basic things you need to know is volts, amps. The units of measurement. So capacitor is measured in farads, and an inductor is measured in henries. Okay, so henry is also a measurement of magnetism. So Dear Henry, I think of Dear Henry. There's a song. Dear Henry, is there a hole in the bucket? Dear Liza, we'll fill it, dear Liza. Dear Henry, fill it. So Henry is magnetism, and Henry is also an inductor. And if you put the two circuits together, you put an inductor and a capacitor together, they can oscillate and go charge the inductor, discharge the inductor, charge the capacitor, and it can go back and forth and back and forth. And if you put a diode in the middle, that's how you get a blinking light. You put a capacitor and an inductor on each end with a LED in the middle and put a battery to it, and it will switch back and forth, and it will charge the capacitor. When it's charging the capacitor, there's no light in the diode, and the light turns off. And then when it reaches its full amount, it'll discharge, go back to the inductor, and the light turns on as the current goes back to the inductor, and the light turns on. And then it goes the other direction, so you get it turning on, off. So that's what causes, that's how they create a blinking light. It's called an LC circuit. L is inductor, and then C is a capacitor. So you put an LC circuit with a diode in the middle, and that causes the blinking lights. So that's how they do that. And so you guys can review and study up a little bit more for next week. 3-15 has some schematics. There's a question about what is the definition of a schematic. It's just a standard way of representing electrical components. There's some of those mentioned here. We won't go over those today, but we'll come back next week and do that. All right, so I'm going to pause the recording, and we're going to go into chapter 4. I think that was a little long. I was trying to make it 30 minutes. We went 42.